All right, so everybody got the script for today and the new GLM folder? Cool. All right, so today we're just going to talk about some categorical or some factor stuff. We're going to go back to the Prestige data set, which we should all be familiar with. But if you need a reminder, you can just run that and come over here to the Car Data Prestige, and you'll see that it's that 1970s Canadian occupations data set. So when we look at this, we see that we have these variables that we've used before: the education income, the percentage of women, the prestige, etc. The one thing that we haven't dealt with before is we've never looked at this type variable. And I went ahead and I threw in this as well, just as kind of a refresher of like exploring your data, like looking at those descriptives. And I really like performance analytics for this one particular chart, so that you can get your univariate distributions, your bivariate plots, correlations, all that sort of stuff. So really with just these two lines, you can get a lot of the information that you're going to be looking for. We have this type variable that we haven't worked with, which is there's three levels. It's whether it's blue collar, white collar, or professional jobs. And we want to see if income systematically differs as a function of what category of job it is. So if you're looking for your descriptive statistics, there's the describe by that we used towards the end of last semester. And you can tell it to describe the income by type. And when you run that, it'll break down your results. So we can see here we have our blue collar statistics, our professional statistics, and our white collar statistics. Or in the tidyverse syntax, if you just use group by and say group this data frame by type and give the mean income, standard deviation of income, and the N for each using the summarize function, you can do it out this way. Now, one thing I do want to point out is just keep in mind that the summarize can have some weird rounding stuff. I haven't been able to quite wrap my head around how it determines, because sometimes it'll give you like 1 decimal, and like I haven't. There's if you look on the interwebs, you'll actually see that there are conversations going on about this exact thing that Hadley, Wickham, and them trying to figure out what's the best way to do this. But if it has a period next to it, that's how you know. Like that's dplyr's way of explicitly telling you that, hey, there are some decimal points that were rounded off of this thing. So you see on the end how they don't have periods because those are whole numbers. So just make sure you note if you see the periods or not, and then be aware of things rounding.
That last row, that is what did not indicate the type of job.
Yeah, there are a few NAs in this. Athletes, newsboys, babysitters, and farmers aren't coded for one of these things for whatever reason.
Do you know why that group doesn't show up in the describe by function?
I'm sorry?
In the describe by function, the first way you did it, the group wasn't a group.
Oh, that's probably because the describe by function, like if something is like NA, it just gets ignored in the data, basically. Yeah. Mm-hmm. Yep. So to talk a little bit kind of broadly about factors, this variable is represented as a factor in R, which we have covered before. Categorical variables are different than quantitative variables in several ways. For one, there's no order to them. That white-collar workers aren't a bigger unit than blue-collar workers or professionals. You can move them around, reorder them, it doesn't matter. There's no set amount of spacing between these variables. So the distance between the number 1 and the number 2 is the exact same as the distance between the number 5 and number 6, but the distance between, blue collar workers and white collar workers and professionals, like that, there is no distance there. So just remember, whenever you're working with factors, to think of them as nominal variables. They are different in name only. There is no direction, no spacing, none of that. It's just categories, groups of things. So because of this, it's represented differently in the GLM, whereas quantitative variables use 1 degree of freedom, categorical variables eat up multiple degrees of freedom. And you can think of this as, and even if it was a categorical variable like gender, but you only had, say, males and females, there's only one comparison to make there. So you're using that 1 degree of freedom. Whereas if you have, males, females, transgender, gender fluid, and whatever, like now you can compare this group to this group, this group to this group, this group to this group, these 2 groups to these 2 groups, these 3 groups to this 1 group. There are any number of comparisons that you can make, and each one of those comparisons is an additional degree of freedom. And so that's where the idea comes from of like making these comparisons, these contrasts takes additional degrees of freedom. As far as the number of contrasts, it's however many levels there are minus 1. So if you have 5 groups, there's going to be 4 contrasts. You'll have C1, C2, C3, C4. If you have 3 groups, you'll have 2 contrasts, just C1 and C2. And so whenever you have these theoretical predictions about some groups, it's kind of like, last semester when we weren't dealing with categorical stuff, how we would have our specific like slope of interest or the hypothesis of interest type thing. And so it's basically the same thing here, which we'll work back around to this. But basically we want our contrast of interest to be significant, but that residual contrast to not be significant. And we'll look at why here as we move on. So let's say our predictions is that professional workers make significantly more than white collar and blue collar workers, but white collar and blue collar workers don't differ all that much. We can code this as a contrast to be able to test those 2 hypotheses, with the first being the contrast of interest. So whenever you're making these contrasts, if you see the term a centered contrast, all that means is that if you sum up all of your contrast weights, it should be 0. That's what it means to be centered around 0. And then you also want the ends of your groups, those extreme values, to be 1 unit apart. And I'll just remember that it's like we talked about last semester, and the reason that we use negative half and positive half instead of -1 and 1 is these things, because when you're looking at the interpretations of your regression output, you have to remember that the way you interpret it is a 1 unit increase of whatever leads to a blank increase or decrease in whatever the other thing is. But if your categories are coded, say -2 and +2, where now they're 4 units apart, you have to change the interpretation of that, because the interpretation is still talking about a 1 unit increase, but your categories as they're being analyzed are 4 units apart. So you have to kind of, incorporate that into your interpretation. And the way to avoid that is just making sure that your groups are 1 unit apart, so that you're looking at the difference between, these group means essentially. So that said, the way we would code this is if we make professionals 2/3 and white collar and blue collar each -1/3 to create this C1 variable. In this case, a simple if-else is sufficient. In fact, whenever you have only 3 groups or if you're only assigning 2 values to something, it's very easy to do this. This would work the same if you have, say, 4 groups, but you're looking at like having these 2 groups coded as one thing and these other 2 groups coded as another. Like anytime you only have 2 values, if-else statement is definitely the way to go. Even if there's 3, and you can do a nested if-else where you have, if-else one thing, comma, if-else something else, and then a 3rd value, like we did last semester, which we'll also see down below. There are some other ways of creating these contrasts, and we'll get into them. One thing I'm working on currently is trying to see if there are any new latest greatest functions that do these specific things. I know within the Tidyverse there's a package called Forcats that is like the Tidyverse factor package, and I know it's great as far as like reordering levels, renaming levels, combining groups of things to recode things that way. I don't know off the top of my head if it also has a way of being able to like very conveniently assign different contrasts and stuff. There is some stuff through the LM support package, but I seem to recall Patrick talking a little bit on Wednesday about how like some approaches work better in some instances than the others, and as far as when it's better to use the if-else versus using a more complicated approach. There's really not a good answer, unfortunately. Like so many things in R, sometimes it comes down to, well, just try it. And if you're struggling to get it to work, try it the other way, and you may find it that way. But in this case, if you're only doing 2 or 3 things, most of the time, I'd say probably just a simple if-else will be nice and easy for you. So here we are just going to say to take, if the type is professional, coded as 2/3, else coded as -1/3. And now when we look at our data frame, you can see the corresponding coding for professionals are coded as 2/3, white collar and blue collar coded as -1/3.
Some DF really exclusive.
Yeah, some gives you a sample of your data, a small sample where like head gives you, say, the first 6 rows and tail will give you the bottom 6 rows. Some just pulls like a sample of like your data frame. So then we need to create a second contrast to account for the comparison between blue-collar workers and white-collar workers. So in that first contrast, what we're saying is professional workers, we're comparing professional workers to the mean of blue-collar and white-collar workers. Now we want to see, but what about amongst blue-collar workers and white-collar workers? So here we're taking our professional, we're going to set as 0, and the others will be -1/2 and +1/2. By setting professional to 0, basically what this contrast is doing is ignoring that group altogether, because when you put it in your equation, any professional workers get multiplied by 0. So they just become 0 and basically non-existent. So it's ignoring professionals, and then the -1/2, +1/2. You can think of this conceptually as if you just took this data set, filtered out the professionals, and then coded white collar and blue collar as -1/2, +1/2, and then interpret it just like we did with the quantitative variables last semester, where you're looking at those same things, where your intercept is going to be, the average of the 2, that same type of thing. And so this would be our C2. And what this is showing you is that if you just take these 2 sets of contrast, so this is our first one, and this is the 0, the second one. And if we look at the correlation between those 2, they're uncorrelated, meaning we have an orthogonal contrast here. So here we're going to code that contrast. We're going to make C2 by telling R if the type is professional, code it as 0. If not, then if else type is white collar, code it as 1/2. If not, code it as -1/2. And when we look at sum, you can see the corresponding in our C1 and C2 column, or in our C2 column, we have professionals that are zeroed out, and then white collar and blue collar coded as 1/2 and -1/2 respectively. And so now as far as fitting this model, it works the same way as all the models that we've created before, only instead of putting in, the type as a variable or as one of the predictors, we simply put in C1 and C2. So here we have our income regressed on C1 and C2, and we checked our summary and effect sizes. So when we look at this now with our output, we see that C1 is significant, C2 is not. Now, what is this intercept right here? Well, what is represented by $6,995.30?
The average of the color and white color compared to the professional.
Not for the intercept. You're thinking here at C1. This intercept will be the mean of group means. So all three groups, if you take their averages and average them together, then you're at almost $7,000. This C1 now has blue collar, has professionals coded as one thing and blue collar, white collar coded as the other. So this represents that average difference between professionals and the average of blue collar and white collar. So then what is this $321 here? That slope of C2.
Just the difference between blue collar and white collar.
Exactly. So that C2, it's ignoring professionals. On average, what's the difference between blue collar workers and white collar workers? And earlier I said something about how you want the contrast of interest to be significant and not this one. The reason that that's a good thing is because if you think about it, what this is saying is that yes, professional workers make significantly more than white collar and blue collar workers combined. Furthermore, white collar and blue collar workers aren't significantly different. So we know that this group is significantly higher than these two, and that these two are not significantly different from one another. But when we look at our effect sizes, the difference between professional and the average of blue collar and white collar accounts for about 34% of the variance in income. And you can see that the difference between white collar and blue collar workers account for a very, very, very tiny amount of the variance in income. So as far as going beyond simply saying, this is significantly different than these two, and these two are not significantly different. The other approach that you could take is using linear hypothesis testing, doing those equivalence tests like we did last semester. So in this case, I calculated the pooled standard deviation just to have some number. And so that's 1975.14, the pooled standard deviation of white collar and blue collar. And so then I'm just saying, like, well, if it's less than one standard deviation of these two things, then it's meaningless. So going with that, we use this LHT, and we just tell LHT that we're looking at the C2 parameter and comparing that to 1975 and negative 1975. Keep in mind that when you do these, you divide the p-value by 2. So when we run that first one, 0.011 divided by 2 is 0.006. And the second one is 0.066 divided by 2, 0.03. So what this is telling us is that the difference between these two groups is significantly below the upper boundary, but significantly above the lower boundary of this range of values that we consider to be meaningless. So conceptually, the way to think about what it means to compare something by LHT versus simply looking and being like, yep, this one's significant, and nope, this one's not. That latter version, if all we do is we're looking at our regression output and we say, nope, no significant difference here between blue collar and white collar workers. What we're saying is we don't have enough evidence to conclude that there is a difference between these two groups. By doing the linear hypothesis test and having it significant for both and within that range, instead what we're saying is we do have enough evidence to conclusively say that the difference between these two are meaningless. So think of it as one saying we can't say that these are different, and the other is saying we can say that these are meaninglessly different, if that makes sense. So that's the, I just wanted to refresh on how we use this LHT function. And just remember, as far as the way that you put it in, you just have to give it whatever the exact parameter name is. And so if you run your coefficients, it'll tell you, intercept C1, C2, these have other names. So just whatever is, no matter what the model, one of the nice things about this LHT is that it works with basically any models. And all it's going to do is take whatever name you put in, compare that value to whatever you put in up there. So keep in mind that, if you don't name your contrasts C1, C2, C3, let's say you're working on homework and doing contrasts on, 4 different problems, and you name them C1, C2, C3 in this one, but in this one you name them like CX1, CX2. Just remember, put in whatever your coefficient names is for your model, and then make your comparisons. Just remember to divide that by 2. Together, C1 and C2 fully represent the comparisons that can be made because the contrast of interest is significantly different, and the other we saw with the LHT is significantly within that meaningless region. We can conclusively say that people with professional occupations earn more than white collar and blue collar workers who don't differ in how much they make. We're not going to do this in lab exercise stuff. If you want to look down through it to kind of see what's going on, it's basically figuring out, all right, if you have these 5 groups of things and you want to make these specific comparisons, how might you code these specific contrasts? Because one of the nice things about contrast is it gives you, basically unlimited flexibility in how you compare things, how you group things, and which comparisons you're wanting to make, which is one of the reasons, Patrick loves thinking about things in terms of a priori, planned orthogonal contrasts. But as he kind of alluded to in lecture last week, you got to be careful with it because of that flexibility, it would be really easy to be like, well, of course this would make sense. This is the comparison I want to do. But just keep in mind, if these are things that you should be thinking about before you look at your data, best if you can pre-register and say, hey, I haven't even collected data, but here's the questions that I'm asking. And here's the analysis that I want to do. I want to compare professional workers to blue collar and white collar workers together and blah, blah, blah. So being able to spell out what those comparisons are that you want to do beforehand to keep from getting into some, I won't call it ethically gray area, but analytically and bad sciencey gray areas of after the fact, revising what you're doing based on what your data show you, which is something that you want to avoid as to the greatest extent possible. Do y'all have any questions about anything?
Could you maybe give like a brief example of how to write up the results of the equivalence test?
So for your equivalence test, whichever one is the bigger p-value is the one that you report. So in this case, it would be this one right here. And so what you would report, you would say something along the lines of linear hypothesis testing compared the differences against some value that was chosen that was determined to be uninteresting if the effect is smaller than whatever. As far as the statistics that you report, all you do is you'll report your F degrees of freedom and your p-value from the biggest p-value. So that if that bigger p-value is not significant, then your equivalence test is not significant. If it is, then you go based off whichever one is the biggest p-value. So whichever one is the closest to not being meaningless, if that makes sense. Because the assumption is that if you're always reporting the biggest one, then we know that the other one is going to be even more significant. And so that's not particularly meaningful to us. But so you'll just report it using these statistics from the biggest, but don't forget to divide that p by half. And if you notice down here, it gives like a period where it says that the period is, no, I take that back. I read that the other way, yeah. Either way.
Yeah.
And so that's the statistic that you'll report. And if you don't want to report it as an F, because that would be F parentheses 1 comma 95 equals 3.44, P equals 0.03. If you want to report it as a T, F is just T squared. So take the square root of that, and you can report it as T95 equals whatever, P equals 0.03. But in short, you'll just you'll say that you use linear hypothesis testing to test this difference against this meaningful boundary that we've determined, and then report the statistics from the biggest p-value of the two. Anything else?
For the last ones, do you happen to have the answers to those last questions?
The stuff down at the bottom? No, we'll take care of that next week.
Curious about.
Yeah, it's a little bit difficult. And the thing with contrast that sometimes it can take a minute for it to click and kind of think through how you are making these comparisons. But usually once it does click, there's a lot just oh, got it. Okay, now let me figure out what's my specific hypothesis? Oh, so this would be the contrast that I'm wanting to do. Where things can get more confusing is when you have, it's easy to do two contrasts and make them orthogonal, where you have, 2/3, -1/3, -1/3, and then 0, 1/2, -1/2. That's an orthogonal contrast. Once you have multiple levels where now you have three contrasts that you're doing, and then keeping all three of those contrasts uncorrelated. There's a lot more that goes into it, but that's the kind of stuff that I believe they'll be talking about next week. And then beyond that, these contrasts, it's not just, going to be DV regressed on C1 plus C2 plus C3. Like there's moderation in contrast, so looking at like interactions. So say in this case, we said, well, what about like, does this interact with gender? Or does this pattern of data hold equally for men and women? And so if we wanted to have an interaction of these two contrasts and gender, we would just put that in the model. But that comes down to, we talked a little bit last semester about thinking about like the distributive properties whenever you're entering these models into R. So in this case, if you wanted this to interact with gender, if you just added an asterisk and then gender, or rather, like if you put this in parentheses and then have it interact with gender, then what that means is it'll give you those main effects for each of these things, but then also allow each one of those to interact with this other thing. And so as we get further down the road with these contrasts, the models become a little bit more complicated, but it's all still the basic concepts. And then it just comes down to thinking through, well, how do I enter this so that the distributive properties give me the crossing of the variables that I want to cross without allowing variables that I don't want to interact together, if that makes sense. I believe, I could be wrong, but I believe that if you just put the asterisk and then sex here, that it would give you the main effect of C1, the main effect of C2, the main effect of sex, and the interaction of C2 and sex, but it would not cross over with that C1 sex interaction, which is where, but if you put it in parentheses, then those distributive properties would have each C1 and C2 interact with sex. So we'll be getting into some stuff like that as the semester goes on. I believe, it's kind of at a disadvantage with, MLK being next Monday. So next week there's only one lecture. But I believe that the plan is that like basically the first 3 weeks of the class will just be on these contrasts and stuff. This semester there's a lot more flex time built into the schedule. There's a lot, there's some review time built into the schedule. So I'm anticipating that everyone will agree that the pace of the course this semester will be a little bit slower and give us more time to process stuff. We covered a lot of information last semester. I'd say in that one semester, we covered basically 75% of a typical year's worth of grad stats, which is hectic, to be sure, but it's nice in that it will allow us to slow down a bit this semester, but also get into things that haven't been covered before. He talked about even doing some stuff with linear mixed effects models, with factor analyses, EFA, CFA, so some multivariate-ish stuff, the dichotomous outcomes. So we're looking at logistic regressions and things like that. So we'll be able to get into a lot more this semester. But I think that the pace will be slowed down a lot. But yeah, anything else?
You don't have the answers to these questions?